During this presentation, we have to study the specific heat of gases. First of all, we should know the definition of specific heat. The quantity of heat energy required to raise the temperature of unit mass of the substance by 1 degree Celsius is called the specific heat. The unit of specific heat is obtained by the relation H equal to mc theta. Heat capacity H equal to mass specific heat rise in temperature. Then the specific heat C equal to H by m theta. Heat energy is measured in terms of joule. Then mass is expressed in terms of kilogram. Then temperature is expressed in terms of Kelvin. This is equal to joule kilogram power minus 1 Kelvin power minus 1. This is our SI unit. If you want to express the same in terms of CGS, then C equal to H is expressed in terms of calorie, mass is expressed in terms of gram, then theta is measured in terms of degree Celsius, which is equal to calorie gram power minus 1 degree Celsius power minus 1. This is our CGS unit. In the case of liquids and solids, the specific capacity is fixed. Whereas in the case of gases, we have had two specific capacities. One is specific capacity at constant volume, Cv, and the other is specific capacity at constant pressure, Cp. Here we have given the reason for that. On heating a gas, molecules are expanded and work is done against the atmosphere. Therefore, we need more heat energy. If you apply pressure externally to keep the volume of a gas constant, less heat is needed to increase its temperature. Therefore, a gas has two specific heats. One is specific at constant volume and the other is specific heat at constant pressure. Mathematically, we may write del Q equal to du plus del W. Here delta Q is the quantity of heat energy given to the system. The given heat energy is utilized in two ways. Part of the energy is used to increase the kinetic energy, internal energy of the system, and the rest of the energy is used to carry out some external work. Here del W equal to P dV. You know that work done equal to force into distance moved. Force acting per unit area is our pressure. Therefore, F is equal to pressure into area. Then del W equal to pressure into area into distance moved dx. Area into dx is change in volume. So, P into dV. So, this equation is modified as del Q equal to du plus P dV. Now, we do the first concept. On heating a gas, molecules are expanded and work is done against the atmosphere. Therefore, we need more heat energy. If the heat energy is applied to the system, part of the heat energy is used to increase the internal energy of the system and the rest of the energy is utilized to carry out some work. So, we need more heat energy to increase the temperature of the system. If you carry out this work at constant volume, to keep the volume as a constant, externally we have to apply some pressure. Now, this relation is modified further. See here, del Q equal to du plus PdV. This is available relation. In order to avoid the expansion process, if pressure is applied on the system, now the volume is a constant. This is du by dt. At constant volume, dv equal to 0. Change in volume equal to 0. If the volume is constant, in order to maintain the volume of the system as a constant, we are applying external pressure. So the second term is 0. We may write del q equal to du. Then del q by dt equal to du by dt. Here Cv equal to del q by dt at constant V, which is equal to du by dt. This is called specific capacity at constant volume. And if you keep the pressure of the system as a constant, del q equal to du plus p dv is the equation. Del q by dt at constant pressure, which is equal to du by dt plus p into dv by dt. This is the equation. Now, del q by dt at constant p is Cp. Therefore, the above equation is written as Cp equal to du by dt plus p into dv by dt. Then Cp into dt equal to du plus p into dv. See, keep this equation too. Now, from this relation, using this relation, we can write Cv into dt, just cross multiply, equal to du. Keep this as an equation. Now, find out the value of equation 2 minus equation 1. That is Cp into dt minus Cv into dt, which is equal to du plus p dv minus du, which is equal to p dv. Then this is modified as Cp minus Cv into dt, which is equal to p dv. Then we know that p equal to RT. Then p into dv equal to r into dt. Instead of this p dv, we can substitute r dt. Now the above equation becomes Cp minus Cv into dt, which is equal to r into dt. From this we can write Cp minus Cv equal to r. Here Cp minus Cv, these are all in calories, but r is in joule. We know the unit of r. Joule mole Kelvin. If you want to convert this in terms of calories, it is modified as Cp minus Cv equal to R divided by J. This is called as Mayer's relation. For an ideal gas, the Mayer's relation is Cp minus Cv equal to R divided by J. According to equilibration theorem, energy associated with each degrees of freedom is half kb into t. Here kt, kb, k suffix b stands for Boltzmann constant. Energy of each molecule is half kb into t into f. Here f is degrees of freedom. Now, energy of 1 mole of molecules U, which is equal to half n kb into t into f. Here n is our Avogadro number. We know that R by n, gas constant by n, which is equal to Boltzmann constant. Therefore, n into k equal to R. Now, the energy of 1 mole of molecules U equal to half into, instead of n into this kb, we have to put R. R T into F. This is a general formula for energy of 1 mole of molecules. U equal to 1 by 2 RT into F. We know that CV, specific capacity at constant volume, equal to du by dt. From this relation, CV equal to 1 by 2 R into F. This is the value of CV in general. Now we have to find out the value of CP. We know that CP minus CV equal to R. Therefore, CP equal to CV plus R. Therefore, CP equal to 1 by 2 R into F plus R. This is the value of CP. This is R into 1 plus F by 2. Now we have to find out the value of gamma. Gamma equal to Cp by Cv. The ratio of specific capacity at constant pressure to specific capacity at constant volume is called gamma. Now the value of Cp is R into 1 plus F by 2. The value of Cv is 1 by 2 R into F. This is equal to 2 into 1 plus F by 2 whole divided by F, which is equal to 2 plus F whole divided by F, which is equal to 1 plus 2 by F. This is the general relation for gamma. Gamma equal to 1 plus 2 by F. Gamma equal to 1 plus 2 by F. Here F is degrees of freedom. For a monatomic gas, F equal to 3. Therefore, gamma equal to 1 plus 2 by 3. which is equal to 1.66. This is the value of gamma for a monatomic gas. For a diatomic gas, degrees of freedom F equal to 5. Now gamma equal to 1 plus 2 by F is equal to 1 plus 2 by 5, which is equal to 1.2 by 5 equal to 0.4. 1.4. At high temperatures, the value of F equal to degrees of freedom is equal to 7, because in addition to translation and rotational energy, the system is having vibration energy also. Therefore, at high temperatures, a diatomic gas has the degrees of freedom of 7. So 1 plus 2 by 7. The value of 2 by 7 is 0.28. Therefore, this is 1.28. 285. For a triatomic gas, degrees of freedom F is equal to 6. Therefore, gamma equal to 1 plus 2 by 6. 2 by 6 equal to 0.33, which is equal to 1.33. At high temperatures, F equal to 7, then gamma equal to 1.285. See the formula for CV. U equal to half RTF. U, take that formula. U equal to 1 by 2 RTF. For a monatomic gas, F equal to 3. Therefore, U equal to 3 by 2 RT. Then CV equal to du by dt, which is equal to 3 by 2 into R. Then Cp equal to Cv plus R, which is equal to 3 by 2 R plus R, which is equal to 5 by 2 R. Then gamma equal to Cp by Cv, which is equal to 5 by 2 R into the value of Cv, 2 divided by 3R, which is equal to 5 by 3. We know the value of 5 by 3 is 1.66. Same value we have arrived using this formula also. At the time of writing your answer, you may be expected to present the value in any form. One thing we have to know, the value of Cp is always greater than the value of Cv. Take this formula, del Q equal to du plus PdV. The succeed capacity at constant pressure is given by del Q by dt, which is equal to du by dt plus p into dv by dt. If you apply constant pressure, this is Cp, which is equal to du by dt plus p into dv. Cp into dt, which is equal to du plus p dv. See that if the applied heat energy is used in two ways, part of the energy is used to increase the internal energy of the system and the rest of the energy is utilized in doing some work. So we need more heat energy to increase the temperature of the system. If we carry out the things at constant pressure, we need more energy. Therefore, the value of Cp is always greater than Cv. So Cp by Cv is greater than 1. Gamma equal to Cp by Cv is always greater than 1. It's a general rule we have to adopt.